Hello and welcome to the interim presentation for Team 2 for Class ME452. Our team has decided to do an analysis and redesign of a table lamp. Our team members include Shivastu Kartik, Noah Nisley, Nathan Lang, Noah Mikey, and David Wells.
An adjustable table lamp is a light source with modular light intensity that can be mounted to a flat surface, ideally a tabletop, and positioned with certain degrees of freedom to meet user lighting needs. It is ideally utilized as a supplemental light source. The adjustable table lamp analyzed by our team utilizes springs and extra joints at its head and base to assist in maintaining lighting position. We have chosen to redesign this lamp to both improve user comfort while using the device and to increase the overall rigidness of the device. The primary customer group for this product are general purpose users that simply need a light source, and the secondary customer group for this product are working professionals and hobbyists. To help understand the parts that comprise the selected device, here's an exploded CAD assembly view outlining all components of the device except fasteners.
To conduct a functional analysis of our product, we developed a fast diagram. We began with the task function of the product, which is to project light. To do this, we would have to support the light source and move the light source. To support the light source, we would have to maintain its position and distribute its weight. And to move the light source, we would need to enable movement in the X, Y, and Z axes. We also addressed some supporting functions that would enhance the product. To do this, we would maximize the degrees of freedom to allow the user the maximum possible flexibility in orienting the light. We would enable comfortable positioning to ease the process of adjusting the orientation, and we would add resistance to enable precise adjustments to the orientation of the light. We use the fast diagram to develop our functional component mapping matrix, which correlates the components in our bill of materials to the functives developed in the fast diagram. The most commonly addressed function is to maintain position, with 7 out of our 13 components being involved in supporting this function. Conversely, the head joint is the component that addresses the maximum number of functions, being involved in maintaining position, moving in the X, Y, and Z axes, as well as maximizing the degrees of freedom.
Here is the bill of materials of the lamp. We have the part name, quantity, material, manufacturing process, assembly process, material cost, processing cost, assembly cost, tooling cost per part, and total unit cost per unit, along with the totals of those times the quantity. Points to note include that there are $60 worth of components for the struts and $48 worth of components for the springs, bringing up a total cost of $140 per unit due to unoptimized processing and assembly cost and high component costs. Here is the quad chart with the part name, importance level, low or high, and manufacturing cost, low or high, along with results, either redesign, eliminate, or keep as is. With a high importance and a high manufacturing cost, we are going to redesign it, such as the base. With a high importance and low manufacturing cost, we're going to keep as is, such as the knobs. With a low importance and a high manufacturing cost, we're going to eliminate, such as the anchors. And with a low importance and a low manufacturing cost, we're going to eliminate, such as the head joint.
Here we have two possible assembly sequences that can be used for the table lamp. The first assembly sequence involves assembling the lamp vertically, adding one part at a time. The second assembly sequence involves constructing sub-assemblies and then combining these sub-assemblies to get the final product. It was decided that method 2 is a superior assembly sequence in every category other than ease of locating parts. Assembly sequence 2 involves better grouping of components, which leads to less undesired movement during assembly, and thus is the preferred assembly sequence.
The first step in our product family design is to create a functional differentiation table. This table takes the leaves of our fast or our functives and separates them into two groups, those that are the same between the customer groups and functives that are different between the customer groups. Functives that we've chosen to be the same include maintaining position, distributing weight, and positioning in the X, Y, and Z direction. Functives that we've chosen to be different include an additional degree of rotation between the base and the arms linkage, as well as comfort features for those who will adjust the lamp frequently. Comparing this with the functional component mapping matrix yields us with the component commonality table, a table showing which parts will be common and which parts will be unique to the variety. The modules on the right that we've chosen are the base fulcrum and the knob and will be discussed in the next few slides. Module 1, or the knob, was redesigned to have a larger shape as well as more points. This, coupled with a material change to a 98 durometer TPE, should facilitate more comfort for users adjusting the lamp. The second module, the base fulcrum, was also redesigned. As you can see on the left, the original design contains a tab that limits rotation in the vertical axis. However, the redesign features a slot that allows for 180 degrees of rotation about this axis. It should be noted that this part is very similar to the original design and will likely be able to be manufactured using the same die sequence. Lastly, we have an assembly sequence with delayed differentiation. The top shows the assembly sequence that we saw earlier, and the bottom shows its redesign. As you see, moving assembly steps that have multiple variety to the latter parts of the assembly sequence allows for delayed differentiation. In the sequence on the top, the very first step has differentiation already, and there's no opportunity for delay.